Hello, Algebra 2 kids. Today we're going to work with conditional probability. And our objective is going to be define conditional probabilities and use tables and tree diagrams. We're not going to worry about tree diagrams. To determine conditional probabilities. And then in the end we'll have a formula to find conditional probabilities. Alright. So we'll start with something called the Monty Hall problem, which is an example, a pretty famous example, of conditional probability. And we're not going to get into the mathematics of it too much, but it's basically this premise. You're on a game show and there's 3 doors to choose from. You choose a door. One of the doors has a prize behind it. What's the probability that your door has that prize? Okay, so originally this is the part that not many people have a problem with. Well, you have a 1 in 3 chance of guessing correctly. However, the point of this problem is if the game show host knowingly opens a door for you to reveal, I guess if this was deal or no deal, it'd be like a zonk, okay? To reveal a door that has a goat, basically saying, well, it's not door number 3. And let's say you guess door number 1. So the question here is, knowing this new information, should you switch doors? Should you switch doors? And a lot of students think, well, no. Shouldn't my probability here be, well, I have 2 doors. It should be 1/2 and 1/2. And that's technically not correct. The probability here is not 50-50 because your original door had it's still going to have the same probabilities. You now have new information. You have new information you didn't have before when you made your original guess. So this door is still going to stay at 1/3 probability, but well, you have 2 doors to choose from. This one stays with the original probability because you haven't gained any new information on this door. You just know that it's not this door anymore. So this is no longer a 1/3 probability, which means that this has to take the place of this. We need a probability that adds up to 100%. So this technically becomes a 2/3 probability. So it would actually be advantageous for you to switch doors. Excuse me, I'm using the wrong mouse now. It seems kind of counterintuitive, which is why this problem is really famous. A lot of PhD in mathematics actually disagreed with this originally, but through simulations it's been shown to actually be true. And the reason this is true is because, well, it depends on specific assumptions about how the host and contestant choose their door. The key idea here is that the host knows information about doors 2 and 3, and, well, when they reveal that door, there's going to be more information available to the contestant, us if we're the contestant, about doors 2 and 3 than what was available at the beginning of the game, right away when we chose door 1, if that's the one that we chose. Okay, so the host deliberately choosing to reveal door 3, it adds value to the door that he didn't get rid of. It adds value to the door he didn't get rid of. So it's actually a 2/3 probability. This is an example of conditional probability. What is the probability of something happen given that something already has happened? So we're saying, what's the probability of there being something behind door 1 or 2 given that the 3rd door was revealed? It's not going to be quite as complex as this for the examples we're working with, but it's kind of a famous example of conditional probability. So the definition is that the probability of an event B will occur given that another event A has already occurred. And we're going to use lots of tables today to kind of discuss these probabilities. This is how it's denoted. The way this is read is probability of A given B. What's the probability of A happening given that B has happened? Okay, and we're going to use lots of things called contingency tables or two-way frequency tables. It's just a table that contains data from 2 different categories. And contingency tables and tree diagrams can help you find conditional probabilities. We're really only going to work with contingency tables here today. So we'll move on to an example where we're using a contingency table to find conditional probability. In problem 1 here. So this table here shows students by gender and by the type of school in 2005. We're picking students at random. We want to know in example A, what is the probability that a student is female given they're in graduate school? So if we're given that they're in graduate school, really this is the data we're concerned with. the students that are in graduate school. Given that they're in graduate school, well, what's the probability they're female? And we know that probabilities, it's the total number of possible outcomes in the bottom and the desired outcomes in the top. Well, what are the total possible outcomes in the denominator going to be if we're given that they're in grad school? And well, our total outcomes are just going to be the number of people in grad school, which is going to be 1,349 plus 1,954. Okay, that's going to be our total number of outcomes. And our desirable outcomes are female. Well, how many of those are female? 1,954. So the probability that a student is female, given they're in graduate school, is going to be 1,954 over, you add those together, you get 3,303, which is about 59.1%. So, given that someone is in graduate school, the probability that they're female is 59.1%. There's a probability of 59.1% that a student is female, given they're in graduate school. So, when you're working with these conditional probabilities, you kind of want to address that given condition and use that and let that be your denominator. Basically, you want to determine how many possible outcomes when I'm given a certain situation. And then of those outcomes, what are the ones that are desirable outcomes? Put those in the numerator. Okay, well, what is the probability that a student is female? That's kind of a review here. Well, remember how many total outcomes are there for a student? And this is where you have to add all of the things together, all of the students. So we have to add all the male students in 2-year colleges, 4-year colleges, grad school, and do the same for females. That will be our total number of students. So I guess we want the total number of students and then the total number of female students. Okay, the number of female students, we're just going to add those up. So it's going to be 2,462 plus 5,517 plus 1,954 over, and then we add everything together. So it's going to be the same thing in the denominator, plus all the male students to get the total number of students. Add all that together, you should get 9,933 over 17,472, which figures to be about 56.85%. Okay, so there's a 56.8% chance that there is a female in this student population of all of these schools. Okay, so that wasn't a conditional probability there, but the first part was, part A. All right, problem 2. Americans recycle increasing amounts through municipal waste collection. The table shows the collection data for 2007. What is the probability that a sample of recycled waste is paper? So you have to think what they're asking here. What is the probability that a sample of recycled waste is paper? So we're finding the probability. Well, we're given what? Well, we're given that it's recycled waste. We want to find the probability of paper. So we're saying, what is the probability of something being paper given that it's recycled? And this becomes similar to problem 1, part A. Well, this is going to be, well, given that it's recycled, how many total things are there? And that's just going to be this part of the table. Given that it's recycled, well, how many outcomes are there? And that's going to be, well, 45.2 plus 7.2 plus 3.2 plus 2.1 plus 21.7. So that's how many outcomes there are in the recycled. Well, given that it's recycled, what's the probability of it's paper? Well, paper is 45.2. So we have our total number of outcomes for just the recycled portion, because remember, we're given that it's recycled. We're saying, what is the probability that something is paper given that it is recycled? And we're going to find, well, 45.2 over all that stuff added together gives you 45.2, or 45 and 2/10 over 79 and 4/10. Plug that into your calculator. It's approximately 56.9%. 56.9%. So there's a 56.9% chance that given something is recycled, it is paper, or you could probably say in a more sensible way that, well, the probability of something being paper, given that it's recycled, is 45.2 over 79.4. I've kind of been misspeaking. What is the probability that a sample of recycled waste is paper? Okay, so the probability of something being paper, given it's recycled, is that percentage there. So again, when you're working with these, you want to basically find, well, the given amount, how many ways can the given amount occur, put that in your denominator, put the desired amount in the numerator. And it's going to be very similar to finding probabilities as we have before. Okay. Now, rather, when you're not given a table, or maybe you're just given certain values for the probability of an event, you can use this information here. For any two events, A and B, with the probability of A not equal to 0, because then we'd be dividing by 0, that'd be an undefined value, you can't have that. Well, the probability of an event B occurring given A is found by finding the probability of A and B over the probability of A. And in general, to find the probability of A and B, that's the same as doing the probability of A times the probability of B, all over the probability of A. Okay, but keep in mind, this is in parentheses. We have to do this multiplication first. So we can't just divide out that A. And another thing to keep in mind, when you're finding this, this means that you can't do this probability here if you have non-independent events. So it has to be independent events to do this formula. Okay? Now, we're not going to necessarily have to use this formula, but it's just given by the probability of A and B divided by the probability of A. So, in problem 3, a utility company asked 50 of its customers whether they pay their bills online or by mail. What is the probability that a customer pays the bill online, given that the customer is male? So we're saying, what is the probability that the customer pays the bill online, given they're male? So what's the probability we're online, given it's a male paying the bill? And that's going to be, well, again, probability we're online, given we're male. How many options do we have where they're just male? Well, that's going to be this right here. So how many outcomes are there to be just male? Well, there's 12 plus 8, there's 20. Of those, how many are paying their bills online? 12 over 20, which is 60%. That one's pretty easy to find. You don't really need to use this formula. However, if we did want to use this formula up here, I'm going to highlight it in. Maybe I'm going to highlight it. Come on. I'm going to highlight it in green. If we did want to use this formula, well, what is the probability of online? I'll do this in green actually. What's the probability we're paying online, given we're male? Well, we know that that should be the same as the probability of online and male over the probability that we are, remember, of A, probability of A, well, the probability that they're male. We should get 60%. We'll see if we do. Okay, so the probability they're online and male, the reason you can't just do the probability of online times the probability of male to get that probability A and B like we did up here is, well, is the probability of being online and the probability of being male, are those independent events? Or is there a little overlap? Well, we know that you can be online and male. We know that there's going to be a little overlap here, so we can't just do P of A times P of B, but luckily we don't have to worry about that too much. We can just find the probability that we're online and male. How many total outcomes are there possible for this probability to be online and male? Well, there's a total of, 12 plus 8 plus 24 plus 6. There's a total of 50 outcomes. Of those 50 outcomes, how many are online and male? And the answer is 12. So the probability that you're online and male is just 12 out of a total of 50 outcomes. And we're going to divide that by the probability that they're male. Well, the probability that they're male is going to be, well, there's 12 plus 8. There's 20 males out of a total of 50. So it's going to be 20 over 50. We're dividing two fractions. That's the same as multiplying them. 12 over 50 times, well, divide by 20 50ths is the same as multiplying by the reciprocal 50 20ths. These 50s are going to reduce to 1. I'm going to be left with, again, 12 over 20, which is what we had in the first case, and that is equal to 60%. So there's a couple of different ways to do this. You're going to be using this formula to find probabilities when you're given certain values, which is why we wrote it here. And you're also going to be given tables. So that's kind of a very, very quick crash course in conditional probability, mostly using contingency tables and then also kind of by applying that formula there. Just keep in mind, for probability A and B, to use this multiplication idea, they have to be independent events. Otherwise, you should be given a table to find that on its own. Okay, that's all we're going to cover today. It's pretty quick. So, as always, have a good day, everybody. Make sure you're prepared for that quiz and stay safe out there.